last video, we already practice program Kalman filter in C++. So we're using the laser sensor data to update measurement, right? So today we do the same way, but with different sensor data from the radar sensor, from radar sensors. So what difference is between the laser and radar is a value they provide us differently. Laser give us the position x and y, and in the Cartesian coordinate system, but the polar gives us the value in the polar coordinate system. So how we use the polar coordinate system to update the measurement? First, we had to figure what the difference is between a LiDAR sensor and radar sensor. I had a video talk about radar sensor principle later. So today we just see the basically difference between the LiDAR sensor and a radar sensor. LiDAR sensor give up the position, right? And you did it last video, and this is exactly the correct position. And the radar sensors give us the radio velocity, right? And the radio velocity to the direction is toward the object right here in the picture. So, but the radar sensor had the advantage. That's a lower spatial resolution, but the LiDAR sensor very high solution. So the question whether we combine both sensor and to update measurement in the Kalman filter, we call the sensor fusion. So to do that, we do the same way with the LiDAR sensor. In the radar sensor, we also have the state transition function. We use the Kalman filter. We have state transition function right here. We have state vector, and in the state vector, we also have the state variable PSVY, VSVY, and C is the measurement function, right? And we know it's in Kalman filter is the measurement function is a linear motion, right? And omega is a process noise. And rho right here is the distance, the radial distance from the origin, right here to the object rho. We also have the phi right here is the angle between the rho and the motion, right? The direction of the motion of the automobile vehicle. We have the range rate with the chain of the rho, so we call the rho dot right here, and it is the radial velocity. So in a measurement function, you know omega is a noise. Noise means the Gaussian distribution with the zeros mean, with the mean is 0 and covariant R. Covariant right here, you know in the radar they give you the rho and phi and range rate. So we have the radar measurement covariant matrix in the 3 by 3, right? We remember in the 2 dimension we had 2 by 2, right? And you know we have the measurement from the radar sensor give us the rho, the distance from the origin to the object, right? That's the radial distance, right? And the phi, the angle, and the radial velocity. But the state variable right here, you have the PSPY, VSPY, the Cartesian coordinate system, right? So what the function H for mapping from the Cartesian to polar coordinate system. So we had to thinking how to get that function, measurement function. And the measurement function right here, you already know that. I think you know that from the calculus 3. How about you learn from the polar coordinate system, the relay between the Cartesian and polar coordinate system. So we can got the value rho equal ps prime square py prime square, right? and phase attention P from PY from and PX from and Rodolph from this formula. Okay, this is deploy. The range rho, the distance from to the pedestrian, the range is basically the magnitude of the position vector rho. We can define rho right here and tension PY/PS. If you don't know, you can look at the right here. You can say rho, okay, PS PY, okay, and VS VY right here, and you geometry you can get the relation between the coordinate and the polar coordinate system. So the measurement function is composed three components. So to show how to predict state, so we have the state variable. We have the four variable right here. For state variable right here, it mapped into the measurement space z. Z from measurement from the sensor only rho, v, and rho dot, right? That's the reason we have the HA function to map in between two coordinates. So in general, we have the measurement function to map in from for state variable right here to 3 from measurement, right? From a sensor measurement, right? And after we already have the H function, so we know this function is a nonlinear function. So from the extended Kalman filter, we already learned about extended Kalman filter applied for nonlinear function. We have a Gaussian input, and for the output with nonlinear function, we got the non-Gaussian distribution. So that's the reason we cannot apply for Kalman filter, right? Input and output had to be linearly, right? So we apply the Kalman filter. So how to do that? I think you remember the extended Kalman filter video. If you don't remember, we go back to see. I talk very clearly how to apply extended Kalman filter. For example, right here you have the Kalman Gaussian distribution. Okay, you got a sample from Gaussian distribution. You threw the back into the non-Gaussian distribution right. You pass to the function, nonlinear function right here. You will get the non-Gaussian distribution. So we cannot use the Kalman filter in this case, right? So how we solve this problem? We apply the Kalman filter, extended Kalman filter, use the linear approximation, right? We in small section here, you can do the apply the linear approximation using the Taylor series, right? And if you know Taylor series, you go back to the video and can see that, and you can get first order of Taylor series. Right here is the linear function, right? For the measurement function, right? And right here, if I write it right here, if you have the state transition function in prediction step, have the nonlinear function, you can use the same thing for the measurement function right here, right? To apply for measurement update, right? So I bring here to have you remember to apply the extended Kalman filter right here. If standard Kalman filter, okay, for the linear function, but if it's non-linear transition state right here, function right here, we apply to the extended Kalman filter, and we apply the Jacobian to find the f, right? And in similar way with the measurement function right here is non-linear function, non-linear motion, we can apply the extended Kalman filter, right? And right here we use the Jacobian to find h to update the measurement. State variable update and the covariant update. Just remember, remind you a little bit about that. When we apply the linear approximation, for the measurement function, and we got the result is the Gaussian right here. You see the input Gaussian, the output Gaussian. We use the linear approximation, the first order Taylor series, to help us to do that. And in the first order Taylor series, this part derivative function measurement right here with the s, so we call this Jacobian. Okay. In the Jacobians, we have the partial derivative. I think you remember in the calculus, and right here, for example, with derivative the first dimension, second dimension, S2, S3, right? And similar way. And for our example, we have this Z right here, rho, right here, range, variance, phi, and brain rate. Rho dot right here, right? So how we do the Jacobian right here? Jacobian right here, we had to be the three rho, theta, and rho dot. We derivative rho with ps, py, vs, py. So we also have the 1, 2, 3 row and 4 column right here. Okay, we derivative row with ps, row with py, row with vs, and row with py. In similar way, we derivative phi with first variable. Okay, so we have the h. Okay, the measurement function right here, and the measurement function right here. After we do the map, I think the map right here is really complex. We do a lot of derivative here, and we put all together. We got the h measurement matrix right here is help you calculate the s and y state variable update and covariance update, right? Yeah, I hope you know that. And how to do how to get the result right here. You had to derivative. You do calculation, a lot of derivative in this one. You get the result right here, right? So generally, we have the matrix from the LiDAR sense lesson. H8 is the equation from the LiDAR lesson are actually accomplish the same thing, and they are both need to show the measurement update right here. Y equals z minus the h prime, right? But in the laser sensor, you know, h is a measurement matrix. Is really easy to derive because we have the zero here in Cartesian coordinate system. But right now in the radar sensor, h matrix right now will map the state vector s into polar coordinate because in the radar right here, z is the polar coordinate. So we have to map the state vector s into polar coordinate. Instead, you need to calculate the mapping manually to convert from Cartesian coordinate to polar coordinates, right? And the result is right here. Okay, I have you really good at calculus and know how to understand. Right here is easy. Rho between the polar coordinate and Cartesian. What the relation between coordinate and Cartesian coordinate system, right? Polar coordinate. Yeah. So in the radar we have the update measurement become right here. Y equals z minus h, right? So but in the laser, you remember that's only here. But in the polar coordinate system with the radar, we use this one because it's a nonlinear function. Summarily, we already know two ways. The first, we update measurement with the laser. The second way, we update measurement with the radar data. We already did right above. And one more thing, I want to tell you, this is the important to know how accuracy our methods. We apply the root mean square error. This formula shows you the error between the estimation right here, the position PSPY estimation, apply the Kalman filter, and you minus to the S true value is mean the real value. Okay, but the difference is right here. This value square root this one, the more it's small, it means the high accuracy, right? So we go to Visual Studio to do some example. How to calculate the Jacobian, okay, measurement metric. Use the Jacobian to calculate the measurement metric. Okay, let's remember here. The more important thing, you had to calculate the Jacobian metric. From Jacobian metric, we do the same way for laser. We update the S and P, right? If you already know about laser measurement update, the radar is the same way, but the difference is they had to use the Jacobian to get the measurement metric, okay? Because nonlinear motion, nonlinear measurement. So in this example, you look at this. We use the Janice in Egan library. Okay, we define the function calculate Jacobian, right? And right here, we say, for example, in the previous state, we have that value. To say the time, we say we already know the predict step, and we got this value is predict step, and through the Jacobian, how we got the measurement. It means you had to calculate h, and after that you plug it into a lot of the formula from Kalman computer formula, and you got the update. But right here, we know the Jacobian right here, the 3 row and 4 column, right? And we have the PSPY, PSPY. The Jacobian right here, you see all value PSPY, PSVY, right? So we say S state right here, the vector right here, the 1, 2, 3, 4, they get 4 value right here, PSPY. And to simplify the Jacobian, the Jacobian right here, the computer geometric right here, we calculate outside. For example, C1 equal PS square, PY square, or C2 square root C1, because we don't want to write all of them into the matrix quite completely, so we can calculate outside and put it back into the Jacobian matrix. It's help you, and we return the Jacobian matrix H right here. That's practice how to do, help you to how to know do the function calculate Jacobian. Okay. Here the answer we give us the Jacobian matrix right here, right? Very easy, but perhaps you really understand. But before you coding, I hope you have to understand the basis right here how we need the Jacobian in this way, because we apply the extended Kalman filter right here. For measurement function, if it's nonlinear, you have to apply extended Kalman filter. And how to apply? We use the Taylor series first order, and after that we use the Jacobian to get the measurement matrix here, right? And the one more thing I want to show you is right here. Right here we calculate the root means. Okay, it means the difference between the value we estimate and estimation and the route to its real value, how the accuracy with Kalman filter, right? For example, we have the estimation right here. Okay, with and right here is route to is the real vector, right? So we apply, for example, we apply the Kalman filter, we find the estimation right here for okay, we have the PSPY, okay, and we also have the route to vector is a real value. So we compare the estimation and route to value, how the difference is, right? We just apply the formula. And you see, if the estimate size and route to have to be the same size, different size, return error, right? So if the same values we apply to the formula, we calculate right here with this formula to see this value had to be really small. It's smaller value errors right here. It means our method is high accuracy. So you see, we calculate a residue between the estimation and route 2. After that, we square root and we divide square root right here. Okay, it's always the same into the formula, and it's return the value. Okay, we got the result right here. This value is 0.1. Okay, between estimation and the real value. Okay. So that's all the methods, all the steps we watching from last video to this video. You can understand how to combine the two, laser and radar to apply for the Kalman filter. And That's it. It's crazy, understand, right?